let's do some practice with Bernoulli. So you pull a random card out of a well-shuffled deck of 52 cards. Note that that's just one card. What is the probability that you pull an ace card? So the reason this specific scenario is a Bernoulli random variable situation is because you're only pulling one card out. So you're only doing one thing. If you were to pull out 5 cards or 13 cards, this situation would be a hypergeometric random variable. But we're only pulling out one card. So the probability that we pull out an ace is 4 out of 52. That's it. So whenever you're doing something one time, calculating the probability is just the number of aces over the number of total possibilities or total cards in this case. And so similar with like another situation, if you were to like roll a die one time, if you were to roll that die 10 times, for example, then the situation would be binomial. But because you're only rolling a die one time in this situation, let's say we want to find out the probability of getting a 3. So that little thing. The probability of getting a 3 is just 1/6 because there are 6 options. You do it only once, and that's it. So probabilities where you're only doing something one time are really straightforward. Situations like that are called Bernoulli random variables. And if you get a Bernoulli random variable question, don't overthink it. The probability is just exactly what you might think it is. So yeah. Okay, let's do a practice example for the binomial distribution. You roll a fair 6-sided die 10 times, and we're going to let X be the number of times that you roll a face with 4 dots on it. This is a binomial scenario because all of the rolls of your die, each one of the 10, are independent in that the result of one roll does not affect the result of another roll. So before we do the probability that you get exactly 2 rolls of 4 dots, we're going to do a preliminary exercise. I want you to think about how we would calculate the probability that you get 4 on roll 1 and roll 5 specifically, and a non-4 on all of the others. So the probability of getting a 4 on roll number 1 is 1 out of 6. The probability of getting a 4 on roll 5 is also 1 out of 6. And the probability of getting a non-4 on the rest of the of your rolls is exactly 5 out of 6 for all of them, right? So I'm going to write that out. And so to calculate the probability that you'd get exactly 2 4s on roll 1 and on roll 5 and a non-4 on all the other positions, you would just do 1 over 6 to the power of 2 multiplied by 5 over 6 to the power of 8. This is the probability of getting exactly 4 on roll number 1 and number 5. And something else on everything else. Okay. So now moving on to part 1 is the probability that you get 2 4s in any of the positions. So it could be on rolls 2 and 3, or 2 and 4, or 2 and 5, or 1 and 5, or 7 and 8. It could be any of the 2. We would only add one thing actually. We would add this thing and choose K, which is equal to 10, choose 2 in this situation. And all we would do is take this and multiply it by that. And that would be the probability of getting exactly 2 2s or 2 4s in general. And the reason that these two answers are related is this one is the probability of getting 2 4s in 2 specific places that we're specifying. To get 2 4s in any of the 10 places, all we would do is multiply it by 10 choose 2. And 10 choose 2 is just the number of combinations of 2 that you could pick from the 10 positions. So like roll 1 and 2, roll 1 and 3, roll 1 and 4, da 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 da, to all the way to like roll 10 and 2, roll 10 and 3. That's all it is. And it also does not include, it doesn't double count things. So like 1 and 2 would be counted, but 2 and 1 would not be counted, because that would essentially be the same thing. So this number is the number of unique sort of pairings of the numbers between 1 and 10, where you could pick 2 numbers. And so you're multiplying the probability of getting exactly 2 by the number of ways that you can pick 2 random places. And that's where that number comes from. Now, this equation is the binomial probability, which is p x equals k equals n choose k times p to the k times q to the, or sorry, 1 minus p to the n minus k, right? And so this part is the Chen choose 2. P is the probability of success, which is 1 out of 6. And K is 2. And then 1 minus P is the probability of not getting a 4, which is 5 out of 6, right? Because there are 5 other options. And so that's that. And N minus K would be 8, because all the other ones, besides the 2 that we're interested in, we want to be a non-4. So that's where the 8 comes from. So yeah, that hopefully gave you a little bit of intuition about why the formula is what it is. So yeah, let's move on to part B. What is the expectation of the number of 4s that we'll get when we roll 10 die? So the expectation of a binomial random variable is equal to n times p. N is 10, because you're rolling a fair 6-sided die 10 times. And P is equal to 1 out of 6, because we're defining success as rolling a 4. So the expected number of 4s is 10 times 1 over 6, which is, oh gosh, 5 over 3, which kind of makes sense, hopefully, if you think about it, right? Because if you're rolling a die 10 times, there are 6 different possible things that it could turn out to. About 1/6 of the time, you'll be getting a 4. So yes, hopefully that made sense. And let's move on.